Hey everyone, welcome to video 22-2C. We're working through, again, the idea of independent events, and in Explain 2 we're actually talking about how to find the probability of those independent events. We've talked about how to determine whether they are independent in the last video. Now we're going to be calculating probabilities for the remainder of our time together. So from the definition of conditional probability, and I'm reading here from page 1151, from the definition of conditional probability, we know that a conditional probability is found by the probability of both events happening divided by the probability of the given condition for any events A and B. If we know that those events are independent, what we said was that the probability of the conditional probability there is the same as just the probability of the standalone probability of A. So we're just going to substitute this value here with probability of A, and we get a new formula that the probability of A equals the probability of both things occurring divided by the probability of the given event. And then finally solving the last equation so that we no longer have a fraction, and simply multiplying both sides of this equation here by the probability of B over here and here, that gives us a new formula for the probability of specifically independent events. So events A and B we can say are independent if and only if. You guys, this wording right here is a condition that means that if A and B are independent, then the probabilities work out this way, and also we can reason backwards and say if the probabilities work out with this product here, then we can say that they are independent. So I'm just going to put a little kind of two-way arrow here that this street goes both directions logically. But let's work through some examples. In example 2, we are finding the probability back in our marble example in the very first lesson that we had, very first video of this lesson. We're going to look at the jar with 15 red and 17 marbles again, and we're going to randomly draw one marble from the jar, and after we put that marble back, remember that's key to it being independent, you randomly draw a second marble. What is the probability that you draw a yellow marble first and a red marble second? All we're going to do is basically calculate that probability by saying that yellow is the event of drawing a yellow marble first, and we know that that probability is 17 out of 32 from before. And because the first marble drawn is replaced, then the probability of red, given that we've already drawn a yellow, is the same as just the probability of red, which is 15 out of 32. And so what is the probability that you draw a yellow marble first and a red marble second? Circle that word "and" again and connect that to that symbol, remember, the intersect symbol. The probability of the yellow and then the red occurring is just simply the product of the two pieces together. So we have 255 out of 1024, and we can get that as a percent with simply working through a division. Working through a division on our calculator, we get roughly 25%. Let's go to the next page. On the next page, we have part B here, which talks about a spinner here with the given numbers that we have on the spinner. What is the probability that the spinner stops on an even number on the first spin and an odd number on the second spin? Well, let's count up the number of ways to get an even number. You guys can see that the even number spots here are 12, 8, and 6. So that is a total of 3 out of our 8 possibilities on our spinner. And because that first spin has no effect on the second spin, remember, the conditional probability of odd, given that we already got an even, is the same as just getting an odd altogether. And of course, if there are 3 evens out of the 8, then there are 5 odds. So the events are independent, so we can use the probability and just multiply the probabilities together. And so we get 3/8 times 5/8 is the same as 15 out of 64, and convert that to a decimal and then a percent. We should get roughly 23%. I want you guys to do the your turns here on this page, please. So numbers 6 and 7, calculating the probabilities of those independent events. Take a pause on the video here. We're going to finish up on the last pages next. Okay, we are on page 1153, and the last part here of this video 22-2C is going to be how we show that events are independent. We've talked about what they are, we've talked about how to check whether they're independent, and how also to calculate the independent probabilities. And now we're going to talk about how to show that those events are independent. So remember back in the previous part of this video, we talked about that this definition here, the probability of independent events, I said this was an if and only if situation, which remember means that the logic goes both directions. So we used it to calculate the probability with the second half of that discussion. But now we're going to be talking about how to kind of reverse the logic and say, okay, now if we can make these probabilities work out this way, then that shows that the independence is true. So again, we started with knowing they were independent, and then we calculated it with the end part, that the probabilities were just the product of the two. Now we're going to say, okay, if we can prove this mathematically, then they're independent. Okay, so that's what we're working on in this video. So let's move this out of the way. Explain 3 talks about here determining from our two-way frequency table again how to determine that these two events are independent. So part A is saying the two events we want to look at is that a patient who takes vitamins and a patient who exercises regularly. Those are my two events. We want to prove that they're independent. So V is going to be the event that a patient takes vitamins, and let E be the event that a patient exercises regularly. We're going to find the two probabilities separately and also the probability of them both occurring and see what the comparison of those numbers is. So there are 60 patients that take vitamins total. So that's 60 out of the 120 total participants or patients in this particular study here. So 60 out of 120 is 1/2. Then we're looking at exercising regularly. That's this row right here, and that is 76 out of 120. So we're going to we're going to take 76 out of 120 and simplify, not multiply. We get 19 out of 30. Then we're looking at that there are 48 patients who are falling into both categories, regular exercise and taking vitamins. And that is 48 still out of the grand total of 120 in that two-way frequency table, and that is 40%. So now step 2 is that we're going to compare those three probabilities. So if we can make it mathematically work out that 1/2 times 19 over 30 is going to reduce to the same probability as the probability of vitamins and exercise together, then we can say that the events are independent of each other. But because in this particular case, 1/2 times 19 over 30 is 19 over 60, and that the approximation for that probability is 32%, not the 40 that we got before, then we would say these events are not independent. Let's fill in part B. Part B, we've got our two-way frequency table here. This time we're looking at children who either know how to ride a bike or don't, and who know how to swim or don't. Okay, so let B be the event that a child knows how to ride a bike, and let S be the event that a child knows how to swim. And our task here is to determine whether riding a bike and swimming are independent or not. So the probability of being able to ride a bike, well, there are 45 children in that first column who total know how to ride a bike. And so that's going to be 45 out of the total number of children in the two-way frequency table, which is, of course, 60. And that reduces to 3/4. There are 40 children who know how to swim, and so the probability of swimming is 40 out of 60, or 2/3. Then the probability of both of those conditions, riding a bike and knowing how to swim, well, of course, That's this particular cell of our two-way table, and that's 30 children. So 30 out of 60 is 1/2. Taking those calculations to the next page and doing step 2. Step 2 is to compare those probabilities. Probability of B, recall, is 3/4. Probability of S is 2/3. And if I do the math off to the side, that's 6 out of 12, which, oh yeah, is 1/2. And if you look at the probability of being able to ride a bike and swimming, which was 1/2, that's equal to the product of the separate probabilities. And so in this case, we could say the events are independent. See what you guys can figure out between your turn, please, number 8 and number 9. And we will see you guys in the next class.